Okay, this video is going to be intense. So let's get into it. Chapter 39, Intro to Quantum Mechanics. We're going to start on page 79 in Workbook Volume 5 if you want to have that open. The crazy thing about this, I guess before we get started, is it's going to take me like 10, 15 minutes to go through what I have on basically 4 whiteboards here. And that's almost all the introduction you need to cover both chapters 39 and 40. The rest is pure math practice. So just know you don't really learn quantum mechanics until you do lots of problems. Okay, let's do it. Quantum mechanics. Why is this important? On the atomic scale, matter behaves probabilistically. We talk about wave functions. You'll see this in a minute. Wave functions relate to the probability of an electron being in a spin up or spin down state. Or it could relate to the probability of an electron being located close to a nucleus versus far from a nucleus. Things like that. So, and on an atomic scale, we have to describe these locations of the electrons or the spins of the electrons probabilistically, which is very challenging. But it also, in theory, could open new doors for us. For example, in quantum computing, right? So, okay, let's first review probability basics, okay? So, number one, we're going to call a probability density. Sometimes you'll hear it a probability density function. Somebody else might call it a distribution function or the probability distribution. We're going to call it a probability density. That's capital P of X. Okay, it's just some function. What does that mean? The probability of finding some parameter x, like maybe it's the location of a frog or something or an electron, the probability of x being between two positions is just the integral of p of x from the initial state to the final state. Okay, so you could say, what's the probability of finding the electron between 1 and 2 nanometers? You put the function in here, whatever it is, that might be complicated. And then you go from 1 nanometer to 2 nanometers, and that gives you the probability. Great. Area under the curve, if you will, right? If you had some probability, well, we'll get to that later. All right. Probability distributions are normalized. This is a word you need to know, okay? Normalized just means the total probability of being found anywhere is 100%, or the total area under the probability curve is 1. That just says if you go from negative infinity to infinity, I'm going to emphasize this here. If you integrate over all of space, the total probability of being found somewhere is 1, right? Okay, more on these limits later. In certain problems, we're not going to need to go from negative infinity to infinity because there's going to be certain problems where maybe we only have to go to 0 to L. So this is one of the things we're going to be watching for. More on that later. The average value of x, sometimes we call that x bar. In our new notation, we're going to use these brackets, the expectation value of x, okay? But that's just the integral of x times the probability distribution. You could actually put in a function of x in there and get the average over that function. So mathematically, that is how you do it. It's just a set of rules. Great. How is this going to change when we get into quantum mechanics? All right, here's an example. This example is actually pretty difficult to derive, but we're not going to be deriving this right away. We're going to do some easier problems first. Okay, but this is a good example to learn from. Let's say we have an electron that is subject to a potential energy function given by this dotted green line here. That dotted green line describes the potential energy. And so let's say it's essentially some harmonic oscillator. So you could think of this as like an electron being held by a spring that has some constant. The effective spring constant could be rearranged in terms of m and omega, and just making sure that shows up here. It's close, it's a little light, but that's good enough. We're going to go with it. Okay, it turns out we can do a bunch of math, and deriving this result is really difficult. We're just going to state for you right now, okay, this is a thing called psi, okay? This is a wave function, psi. It's a wave function. The wave function is not the probability distribution. It turns out to get the probability distribution, we multiply psi by its complex conjugate. So basically, if you know a plus ib in complex number theory, the complex conjugate would be a minus ib. Anything with an I on it flips sign. Now, a lot of the wave functions we're dealing with are real. This one is real, all real values. No, so it turns out for a real valued function, that basically just means square it. But more on that later. Okay, this is just an introduction. Again, here's the important part. This psi is called the wave function. This happens to be the wave function of the ground state, which is why this subscript 0 is there. It's the ground state energy wave function. All right. The probability function, you have to square that. So notice, because there's no complex numbers here, we square it, the 2 goes away. Look carefully. Okay. This letter A is called a normalization constant, right? We require the probability distribution add up to 1. So we use the normalization condition, right? The total probability adds up to 1. So we put in the probability distribution right there. This probability distribution, there's P of X, and you integrate it over all space and set that equal to 1. If you use an integral table, you will discover this happens to be the correct value of the normalization constant for a quantum harmonic oscillator ground state function. Yeesh. All right, we could go on and get the average position. Watch out. Look at this carefully. Before, we just stick X in front of the probability distribution. Here is where things are significantly different. X goes in between psi and psi star. So you do not plug it in front of the probability distribution, you plug it in the middle of it. Now at first glance you're like, yeah, but it just moves around. That's absolutely true. But what if you use the momentum operator and get the average value of the momentum? This is kind of sloppy brackets here. Let me clean this up. The momentum operator actually relates to a partial derivative in the x direction. Partial derivatives are easier. We'll figure out how to do that in class. Don't worry. Right? This is the complex number I here. Great. But so notice, if you take a derivative of the function squared, that's going to give you a different result than if you stick the derivative in between the psi and the psi star. So, okay. Basically, almost everything is the same with the following caveats. Usually, we talk about wave functions. To get the probability distribution, you have to square it. To normalize it, we're still going to do the same technique. However, to get average values, we no longer stick the thing that we want to average just anywhere we want. We have to stick it between the wave function and its complex conjugate like this. Great. Okay, and again, you aren't going to learn this until we do lots of practice, and we will. Let's take this one step further. Let me see if I can do this. Okay, the Schrodinger equation. Schrodinger. I don't know, if you want to try and say it correctly, please look up the definition and get somebody that can actually pronounce it to give it to you on YouTube. All right, this is the Schrodinger equation. All right, and so there's a term here that relates to, I don't know if you can see this is p squared over 2m, right? If the momentum operator is IH bar ddx, when you square that, you get a minus sign, you get an h bar squared and a d squared. But then if we divide that by 2m, that's momentum squared over 2m. Well, think about that. Isn't that k equals p squared over 2m? It is. So that's the kinetic energy. Potential energy, that was our 1/2 kx squared for our spring constant. All right? Well, it seems reasonable that if you operate on the wave function with this kinetic energy and potential energy, hopefully you get the total energy. So only certain stationary states will produce an energy eigenvalue. And so we're going to focus on wave functions that satisfy the Schrodinger equation. Not all wave functions would do this, but they wouldn't be useful wave functions to us. Usually what we do is we describe arbitrary other wave functions in terms of wave functions that meet this criteria. In linear algebra, you'd say, we're going to make a set of basis states that are stationary states that obey this equation, and then we can generalize and create other wave functions out of those basis states. Great. And as a kicker, what about the uncertainty principle? Well, we're going to rewrite that. Instead of delta x, we're going to say the standard deviation of x, so to speak, and the standard deviation with relationship to momentum is greater than or equal to h bar over 2. So how do I get sigma x? Well, this is just a statistics problem right now. Look carefully here. I just want to emphasize where the squareds are. Notice, this gives you an idea of the kind of attention to detail you need to have when we're doing math problems in this. You need to pay close attention. Is the squared inside the bracket or outside? Makes a huge difference in the calculation, right? This one is 0, and yeah, this one is not. Okay, similarly, the standard deviation in terms of momentum would be, and again, I'm going to emphasize where the squareds are, inside the bracket, outside the bracket. Great. And here again is the momentum operator. So you're gonna hear me talk about operators. Basically, operators are the things that we're oftentimes averaging in the wave function equations here. All right, so that's the Schrodinger equation. One last thing. Everything I've been talking about here, on both of these boards, and this one over here, let me just get this in here. Sorry about that. Everything that you have seen me talk about up till now has been one-dimensional, right? dx. We're talking about x. Everything in here had to do with one-dimensional problems. So basically, something constrained to move along a line. In the real world, sometimes we're going to deal with things moving in 3D, like maybe a hydrogen atom. So let me just show you that real quick. So in 3D, and this is basically the chapter 40 problems are in 3D. And so there's a little difference here. In 3D coordinates, right, you'd have to think there's a dr, d theta, d phi, and that essentially when you do the Jacobian, if you don't know what I'm talking about, basically you get a 4 pi r squared in there. And so your probability distribution has to have that 4 pi r squared in it, otherwise you can't normalize it. Right? It won't be properly normalized. And so 1 is no longer equal to the integral of psi star psi. It's equal to the integral of psi of r star, psi star of r, psi of r times 4 pi r squared dr. And when you're getting your expectation values, anything with these brackets is called an expectation value, right? When you're getting your average values or your expected values over the whole range of the function, right? Here, we're going to be sticking in that 4 pi r squared. Limits. Think about this. What's the smallest value of r you could have? 0. What's the largest? Infinity. So notice you can get different limits. And that's something you'll see. Basically, different types of problems will have different limits depending on whether it's 3D or 1D or whether it's 1D with some extra constraints like being trapped in a box or something of a certain length. So the things to watch out for are basically your limits. Do you need this 4 pi r squared? And very carefully doing the order of operations, is something inside a bracket or outside, etc. That's basically it. Now we just need to practice forever. All right.